let's go ahead and get started. Since the students have been working on the project for a long time and there are some common elements to what they did, I thought that what we do today is I'd give a brief overview of the project motivation and some of the methods that the students used in common, and then turn it over to each of the 5 student groups to give you a little bit more idea on their individual assumptions and the findings that they had. Just to sort of begin things, I think I should really mention how hard the students have worked on this. I think if word gets out how much time they spent on this project, I'll probably never teach this class again because no one would ever enroll in it. They've really done a great job, and I'm extremely proud of their efforts and think that they're going to really give you a sense for that today. But just to review a couple of the specifics, when you joined our class at the beginning of the semester and gave an overview of the project area, the scenario that was introduced is that there is an area between 9th and 10th Avenue and between about 2nd Street and 7th Street where consistently there are backups in the combined sewer. And so the combined sewer runs from the west towards the east, and the storm sewer runs from the east towards the west generally, and then discharging south towards Four Pole Creek. And so background on the problem is that, as it should, there are individual connections into the combined sewer of homes discharging wastewater, but unfortunately there's also roof drain stormwater connections, and this reduces the capacity that's available inside the pipe for wastewater during wet weather events because there's this combination of both wastewater and stormwater. And so these roof drain connections are sort of the motivating question and the motivating problem. And when it rains, the water runs off of the roofs. Roofs are generally very impermeable. That's sort of the point of a roof, is to keep the water out of people's homes. And so when it does rain, it concentrates very quickly and discharges to the combined sewer with a quick peak. The pipes fill up, meaning that there's no more capacity and the water has to go somewhere, and one of the places that the water goes is into people's basements, and that's when it causes a lot of damage and inconvenience for them, an extra expense for Huntington Sanitary Board. And so your motivating question was, what if some of these pipes were disconnected? What if the roof drains are disconnected? Would that alleviate the backups? And this is just a schematic showing what if some of these roof drain connections that go to the combined sewers were instead redirected to flow into people's yards, over the surface, along the gutter? Would that reduce the backup that's happening in the pipe? And so that's the motivating question that the students have explored. Just a bit of overview of what their background was. They spent a lot of time in the field characterizing the surface, and this was actually at the individual house level, going lot by lot and determining with a visual inspection whether or not that house had a connected roof drain, and estimating the area of the lot using the county GIS maps, using Google Earth, and estimating the roof area, the percentage of the lot that may be impermeable surfaces like concrete, grassy area, yards. And so there was a very detailed characterization of every lot and property at the surface and trying to estimate what direction the waters will flow. Then moving on to the subsurface, an analysis of the pipes in the area was done based on the GIS data set that Huntington Sanitary Board was able to provide. And so they analyzed every pipe in the network, looking for its characteristics like the slope, the material type, the diameter, and this is the basis for the information that was later put into the main program that was used for simulation, StormCAD. And so StormCAD allows you to assign a contributing area that flows into a catch basin, and through simulating a storm and adding the flows that would already be there from wastewater, compare the capacity of the pipe, how much water potentially it can handle, to how much water would be there during a certain wet weather event, maybe a 2-year storm or a 5-year storm or a 10-year storm. So that's the method that was used, and ultimately what they were trying to do was fill in an analytical matrix, looking at what's going to happen during present conditions, simulating the existing case, when will the system fail, and then looking at if certain disconnections occur, 40% of the homes, 80% of the homes, then will the failure rate reduce? And so I'm really excited to have the students show you their results today. That's just it for the brief overview that I have, and I'll turn it over to the first student group to give you an idea of their analysis and their results.
Good morning. I'm Andrew Keffer, and in this group also is Michael Kennedy and Austin Cox. When we were working on this project, we were getting ready to make our model perform analysis. There were some gaps in the data or other issues we ran into where we had to make assumptions in order to proceed with the project. And some of the slopes of the pipes in our storm sewer network where the pipes had a lower invert elevation at the beginning than at the end. So we had to adjust the pipe invert elevations, minimal adjustments, to allow for gravity flow in the pipes, because our main focus was the combined sewer pipes, and we thought it was okay to change these a little bit to make the model work. And we also thought it was important to account for domestic wastewater, both from houses and from a school in the project area, and the combined sewer pipes. So we assumed some flow per person per day and a number of people in those areas. And when considering flow from a connected roof down the gutter and into the combined sewer, we were unsure exactly what path that took. So we connected each of the 4 blocks into the combined sewer at the same location. You can see here's one block, and here's the flow from each section of connected roofs going to the combined sewer at the same location. And we were not certain exactly how to deal with the road surface flow, and so it was all paved either with asphalt or with brick. So when we used the rational method, we assumed a runoff coefficient C of 0.9 and just used a scaled area. So that told StormCAD that whatever area we drew the catchment, this green block here is the road, that's what area it used in this flow calculations.
Thank you. All right. Our analytical methods. First, to start off, I'll talk about how we set up our model. And as you can see here, we have catchments drawn for surface flow for each block, and they're divided according to contour elevations. We found the contour elevations from Google Earth Pro, finding the high points and which direction they would go. So this section all was at one slope direction, and it would eventually feed into this catch basin along with these here in similar patterns throughout. And then our connected roof flow distribution, as Andrew talked about, is those respective catchments for the surface flow made their own catchments for the connected housing, and they would flow together into one pipe that fed into the same transition of the combined sewer system. And after setting up the model, we were allowed to analyze, and first step was to find our time of concentration. We used the Federal Aviation Administration method, and this was chosen because it was the simplest method with no data that we had, with avoiding gaps or assumptions. It only utilized the C value, runoff coefficient, the channel length, which was found Google Earth Pro once again, measuring the far corner of the catchment to the catch basin, and the slope, which was just the elevation change. And then following that, I'm going to skip out of order here and go down to our rainfall data. And we used the precipitation frequency data server from NOAA's website, and it generated our IDF curve for the 2-year through like 100-year storm, and we only utilized up to a 25, and it used the Hydro 35 spatial distribution data from NOAA as well, from their National Weather Service. And then our disconnection pattern, after we ran the simulation at present conditions and noticed that everything failed, we decided to find a better picture here. Disconnect these respective small darker green areas, which is the connected roof, as I mentioned, according to area and percentages, finding 20%, 40%, 60%. And we tried to distribute equally upon doing the percentages on each block. So one here, here. And we didn't have any down here for the 20%, but the 40% we did. And then 60 we went through and found, or 40 we also went on the other side of the alley to try to equal distribution, everything. And for the strategic disconnection, we tested whether or not upstream or downstream would be a better result for focusing our future disconnection emphasis. And upstream was found to drastically minimize flooding in basements and in the pipes over the nodes. And then our disconnected flow, we had to determine, once we did disconnect it, where does it go? So we assumed that it would flow from the roofs of the houses through their downspouts into the yard, and then follow the same path as the surface flow into the catch basins. And this would decrease the C value for the overall roof from about 0.85 to some lesser value we didn't calculate, but it would overall raise the weighted average of the overall catchment for the surface flow a significant amount. And this allowed us to determine our matrix, as Dr. White mentioned, and find our results.
All right, when analyzing, what's the
Point is top.
Oh, crap.
Press the escape button on the keyboard.
That is.
Top button.
Sorry. Okay, when analyzing our results, we decided to break up the combined sewer pipe into 4 different pipe segments, pipe A, B, C, and D, seen here. You know, each pipe corresponds to that particular block of homes. Here you see the present condition model under a 1-year storm. This red area is denoting the areas where there are failures or flooding with that pipe. And as you see here, under just a 1-year storm, there is flooding in all 4 pipes. That would be a problem. Here is a table summarizing which pipes are failing during what storm is being run and under the disconnection status. That can be a little hard to follow, so we'll look at the figure. Here, this relates the percent of pipes failing to the percentage of homes disconnected. And as you would expect to see, as the percent of homes disconnected increases, the percent of pipes failing goes down. Around 60 or 80% here, you see that the number of pipes failing really, it reduces here. You can see a reduction. Focusing in on the most common, the 1 and 2 year storms, right here, at 80%, there is no flooding anymore. Our model revealed that, as Michael mentioned, that the western blocks, blocks A and B over here, they seem to control flooding more than these blocks over here. So we would focus efforts at disconnecting homes on these western blocks, blocks A and B, and we think that'd be more effective. That's basically what we saw in our model.
Questions?
I think what we'll do is leave all of the questions and applause to the very end, and so that we can have the other groups load their presentations. And the way the microphone's oriented, I think I might tip it just a little bit more. Try and stand here as you're speaking so that the microphone is able to pick up your voice.
Good morning, I'm Jessica Meadows and I'm Carissa Hansen, and we decided to get grouped together and work on your project here. First thing we'd like to talk about are the uncertainties and the assumptions. The first problem we had were some of the pipe slopes weren't known, as the other group mentioned, so we took the data that was provided and just assumed a straight line connection to fill in those gaps. Another thing that we needed to think about was the wastewater from the homes. So we assumed 140 gallons per capita per day for worst case scenario, and that there were 4 people per house because national average is 2.5 kids or whatever, you know. And then also we had C values for the drainage areas was a large assumption. And a lot of it came from the way the entire collective group got their areas and their C values, using weighted values to account for how much was disconnected impermeable going to the land flow.
To get our IDF curve to put into StormCAD, we obtained our precipitation intensity data from NOAA's PDFS website, and we used that to create curves for 1, 2, 5, 10, and 25-year storms. And to get our time of concentration for the overland flow, we obtained soil data from the NRCS website, and we found that it was wheeling type soil, which we then went onto the DEP website and found the curve number for that soil type. And then we used the SCS lag method in StormCAD to estimate the time of concentration for roofs. We assumed 1/4 of the time of concentration for the overland flow. This was because most of the homes were in the middle of the lot, and we assumed that since the water would be running off the roof through the gutter, it was a smoother material, so it would be quicker. And to disconnect our homes from the combined sewer, we just evenly distributed across the network because we didn't know who would be willing to disconnect their homes.
So once we got our network fixed up, we decided to do individual homes instead of large block areas. Down here, this is the school, which does not have any storm water going in to the combined sewer system due to their detention pond. So we only had sewer coming from them with, I think it was 900 students now. As we produced our model, we found that having just a single catch basin was the easiest for keeping the pipe at the correct slope, but it did produce excessive amounts in one location, kind of messing with the model a little bit. So here in the beginning, we tried to kind of separate them a little bit so it wouldn't have such a gush at once, but it messed with the slopes of our pipes so much that for the rest of the network, we didn't do that. This is our 1-year storm on present conditions, and as you can see, it began failing after the first block. So we kind of thought that might be wrong at first because a 1-year storm didn't seem that bad to us, but Dr. Wade explained that that's the worst storm of the year, and Huntington does flood that frequently. So I think that about covers how we decided to generate them.
So when we disconnected all of the homes from the network, you can see at the end of the 500 block, the combined sewer is only receiving domestic wastewater, and we're only at 12% capacity. And then when you get to the 600 block, there's a huge increase in the capacity, so that led us to focus further in on the 600 block. And what we're looking at is all of the overland flow for the lower portion of the 600 block is going to this catch basin, which then is directed into the combined sewer. So in our strategic disconnection, which Jessica will talk about, we're going to look at changing where this overland flow is routed to.
When we decided to go ahead and do our strategic, we looked at all of the data from all of the 20, 40, 60, and 80% disconnections. 60% disconnection did show a significant decrease, but it was still at like 90% when you got down here to the 600 block. Oops, hold on, sorry. Down here. So we decided to go with 80% disconnection just for a factor of safety because this is only a 1-year storm. So from the Google Earth data that we looked at, like she said, we thought it went to this catch basin. So we decided to say, well, what if you just block that one off? No overland flow can go into it. So everything would have to be redirected to 196 here. And in that case, we kept the 80% disconnection and just rerouted flow. And you can see here that on the 1-year storm, that produced significant, well, this is prior to moving in. We had 50% capacity here, but then it jumped drastically. So then after we move it from this combined catch basin to the storm catch basin, we didn't have such a drastic change. Now you'll notice here that it still says 109%, and I believe that this is due to the single catch basin that I talked about earlier, where it doesn't actually come into the network this way. but this provided an even slope for our pipe. So we like that. And then this is our 25-year storm. Previously, we've only shown you 1-year storm effects. This is a 25-year storm, and even with moving this to the next catch basin, it does not fail. It's very close, but it does not fail.
To sum things up, we said that even with 100% disconnection of the homes, the 600 block still failed. So this led us to further investigate the 600 block, and we decided that the overland flow on the lower portion was the main problem. And with an 80% disconnection, it would satisfy current pipe capacities without failing if the overland flow is rerouted to the storm sewer. But we also thought that a more in-depth analysis of the storm sewer should be executed, since it's going to be taken from the combined sewer into the storm sewer. So the storm sewer could possibly fail. And that's all we have. Thank you.
Excellent. I'm glad the students remember what group of quarters they're supposed to be in, because I don't. It could really be discombobulating. To be honest.
Hey, my name is Lee Camp. This is Andrea Markham. We're just going to give you our take on the project here. I hope that I'm hitting the right button now. Okay, there we go. Okay, so just like the previous folks, we went and got our rainfall data from NOAA's Precipitation Frequency Data Server. We, of course, like everybody else, divided our area into surface catchments to delineate whatever rain falls in a particular area goes to a particular catchment. So you know whenever it rains where that drop of rain goes in the catch basins. When we looked at everything, of course, we're including the houses, the lots, sidewalks, roadways. We also had an assumption that roadway crowns were not overtopped during surface flow. So this basically means that water wasn't going to cross the street to get into a catch basin. Next, we want to consider that our focus is the combined sewer and not the storm sewer. We want to also note that we grouped our houses in lots into groups of 5 or 6 generally. Some were less, but no more than 6 houses together. When we had our even distribution of roof disconnections, that was even distribution through the whole area. So when we say 20% disconnection, that means 20% of the roof area's rainwater was being diverted from the downspouts into the pipes, diverting from there to the catch basins, going to the storm sewer. Excuse me. Our assumptions here on base flow was that there was 4,200 cubic feet per second base flow for pipes 744 and 746. These are the 2 main pipes. I'm going to go ahead and point it out here. These are the pipes flowing on this far east end of the area, and it brings water out of the our area of interest. Let's see, where was I? Okay, then we had our population. We assumed 3 people per house and 1 person per apartment. We assumed that each of these folks were generating 1 3/10 times 10 to the -3, so it's a small amount, cubic foot per second of wastewater. And then we assumed that there was a peak flow factor of 6. So that means like first thing in the morning when everybody's showering and flushing the toilet, we multiply this flow by 6. We also assumed for the population of the school that there were about 950 people in the school. That's the students, the teachers, staff, and that these folks were just generating 75% of the standard peak. And I believe,
Hi. There were a couple of areas where it was unclear, based on the GIS data we were given, whether or not surface runoff was contributing to the combined sewer. And so we just wanted to take a closer look at these areas. The first area is, we're calling it Area A. It's on the corner of 5th Street and 9th Avenue. And just to sum it up, our base assumption was that, which one's the pointer? The catch basins here are contributing flow into the combined sewer network, and our alternative assumption is that either those have been sealed off or we misinterpreted the data and they are not contributing to the combined sewer network. A similar thing happened with what we're calling Area B, and Jessica and Chris have pointed that out very well. It's on the corner of 6th Street and 10th Avenue, and it does appear from all information that we're given that these catch basins down here are catching surface runoff and going through pipe 27 into the combined sewer network. We did go ahead and do an alternative assumption and did studies under this alternative assumption as well, which you'll see, where we assumed that either these catch basins would be sealed off or the flow was otherwise diverted to the storm network. So just to sum it up, base assumptions for both areas were that surface runoff does in fact enter the combined network, and our alternative assumption is that it does not enter the combined network at either of these points. And here you can see an overview of our network. You can see here's the two areas, Area A and Area B, that we just spoke about. And the combined sewer, of course, runs right down the alley, as shown in everyone else's network, and then joins with the main line here. And you can see how we have grouped our houses into groups, usually 5 or 6 houses per block, except in the area right here. It's hard to see in this graphic, but right there we did take a little closer look since we were concerned about surface runoff into these catch basins. So we did separate this house, and we're a little bit careful about the way we directed our overland storm runoff flows. And I think Lee is going to talk about what we found.
So here's our 2 tables that show our results. Table 2 shows the results for our base assumptions and what's currently happening now, and then with the different disconnection scenarios. Basically, we saw currently and all the way up to 40% disconnection, all 4 of the pipes that are in between, that are the combined sewer pipes in the alley, will flood no matter what. We started to see changes at 60%, which I think that's the same as rest of y'all. Anyway, we were not able to get, with our base assumptions, any fewer than 2 pipes failing, the last 2 pipes in the 500 and 600 block areas. So that's when we came up with our alternative assumptions. Here, table 3 shows our alternative assumption, strategic disconnections. We looked at 80% disconnection, and we still had 1 pipe fail for a 1-year storm and 2 pipes failing for a 25-year storm. But then when we got to everybody's disconnected with our alternative assumption, then we didn't get any pipes failing. So we considered that was to be our the goal that we wanted, our result. That if we stick to our alternative assumptions, that areas A and B are not contributing to the combined sewer and everybody disconnects their roof downspouts, then we won't have combined sewer failure. But we also agree with the previous group that we should look at storm sewer as well. Thank you.
Hello, my name is Nathan O'Kane. This is Gerald Rowe and Kyle Merritt. We'll get started right away. Here are the current conditions, which you've heard a couple times. We found that 95% of our homes are currently connected to the combined sewer. The combined sewer has a maximum flow of 1.46 cubic feet per second, and the garages, which run along the alley, are, from what we can tell, all disconnected from the combined sewer. And like most groups, our model highly depends on 2 or 3 specific catchments on where overland flow goes. So here's our current scenario right now, where you can see all the houses here are connected to this center combined sewer, like we've mentioned a lot. These lines, sorry it's hard to see, you can't actually turn these lines off, and I'll get to why they're so dense there. The areas of interest, like many others, this is the area we're looking at. This is the alternative assumption for Lee and Andrea's group. This makes a huge difference. So this blue pipe here, there's 2 catchments, that's the combined sewer, and here's the storm sewer. If the runoff from our disconnected houses indeed does go to the combined sewer, then flooding could still very well be an issue. However, if the runoff does go to these storm sewers, it could be an issue, but you might not have backups in the houses. It would probably be on the street. Is this mine? No, that's yours.
Okay. For our methods and analysis, we went out into the field and gathered and tabulated whether the house and garage was disconnected or not. For our C values, actually Dr. Wade covered that rather well. We use weighted values using the roof areas, the yard areas, the sidewalk areas all together with their respective accepted C values. We found our slopes using Google Earth. This is an example of the slope profile from Google Earth of the alley that the combined sewer pipe, or conduit rather, runs down. For our times of concentrations, when the roofs were not connected to the combined sewers, we used the FAA method with the C value and the furthest distance from the catch basin. And when it was connected, we used, for simplicity, 5 minutes. Dr. Wade already covered these quite well. This is a map of when it's 100% disconnected. There's no, as you can see, these houses no longer flow into their respective catch basins. And for the sake of our analysis, we assumed, or we are calling each pipe between the catch basins a separate individual pipe, so that you can get a more dramatic, a more substantial change when you analyze it. The way that we disconnected the roof areas was by area, or the roofs was by area rather than by number of houses. So 20% of the area, we calculated how many roofs constituted that, and then went from there. And as you can see, present conditions, you get 33, for the 1-year storm, you get 33 failure areas. And with just 20% disconnected, it drops by 13. This is our graph that shows that as we disconnect the roofs from the combined sewer system, there we go. There's a remarkable drop in failed conduits, and around 80% is when you get your optimum reduction. We decided to disconnect the houses from the outflow west, because if we started disconnecting from this side, it would fail here anyway and just fail the whole pipe. And the water is flowing this way, so to get a better, more accurate analysis, we went from east to west. During the 1-year storm, present conditions, oh, come on now, there we go. This much of the conduit fails. When you disconnect 40%, it's reduced to this much. Okay.
All right, well, this is the part that we and the engineers like. Do this and you'll fix it. So, we suggest that we close off the catchments right here going into the combined sewer with the corresponding FID numbers, and that will divert the flow to these red basins right here with the corresponding FID numbers. And again, this is on the intersection of 10th Avenue and 6th Street. This prevents the flooding of the combined sewer east of these catchments, so everything in this area they will prevent flooding of. Now, please understand we do not suggest doing this. However, if this is your choice to do so, this is possible. So this is a possible solution. Changing these corresponding conduits with these FID numbers to this diameter, and all of these, excuse me, all of these conduits as of right now have a 1 foot diameter. Again, we don't suggest you doing this, but this is a possible solution. And again, yes. So our conclusion is, it is our opinion that backups in these homes can be prevented, and this is what we have to do to accomplish that. Ground level combined sewer catchments that we mentioned earlier must be closed off, and out of the 91 connected houses, at least 73 of these houses need to be disconnected. Now, this results in the number of backups during the 1-year storm to go from 33 straight to 0. So we like that. And this is less water to treat at the wastewater plant. And yes, this does give a greater risk of the storm sewer backup, but this is better than a combined sewer backup and flooding in your basement. Flooding in the street is better than flooding in anyone's home, by far. So thank you. Please hold questions till the end of the lecture.
Alright, I'm Robert Daniels, it's Thomas Rice. Start. So we had some assumptions when we did this project. We assumed 1.3 times 10 to negative 3 cubic feet per second with 3 people per house. Sounds like about everybody else did that too. We neglected the sewage flow from the school because figured the peak flows from the school would be different from the peak flows from the houses, since you're not, you haven't left for school yet when you're using it at the house. We assumed a slope 0.005%, and we just went with 5 minutes for time to concentration. Some of the storm network elevations were off, but we just assumed elevation since we weren't looking at the storm network anyway. Move this. So we separated every house and every yard and every shed has its own catchment basin to get greater accuracy. Then we put their C values into the respective catchment basins for all of them. And there's what our model looked like. You want to talk about the pipe network?
Sure. We drew it according to the data gathered
rather than doing anything different. I think our only thing that we really did different from other groups is that we assumed in any spot where it was ambiguous whether it went to the combined or the storm network, we assumed it went to the storm. The storm network, we just used our best judgment for all of the holes that we had. And then we created inflows coming from the east and from the south, according to the assumptions we showed on the previous slide. This is our network. We used the map keys that were provided in the GIS data to differentiate pipes from nodes.
We went out in the field and looked at every house to see if it was connected or disconnected from the combined network, and then we could put that in the data for a model where when it was disconnected, we just assumed that the flow would go to the same place the yard was going, which is a pretty fair assumption. But we also assumed all the sheds were disconnected, which it looked like they all were. How we attributed the flow for the blocks, some groups put it, they had to space it throughout the pipes, but we just split the blocks in half so that the east block went to the east node, whereas the west block went to the west. And we attained the IDF curve from the NOAA website.
We disconnected block by block. We split it evenly with each block. And since there were 20 houses for each block, except for the last block, that was 4 houses per block. And we started from the west, not the east. And then we just rerouted the flow to the catch basin, the same place as the yard typically. And this is the present conditions 1-year storm result, just to give you an example. You can see that all of the main conduits are failing because the percentage flow is over 100%. And then this shows for each of the main conduit at each storm what level of disconnection it takes for that pipe to no longer fail. So for a 1-year storm on the first pipe, that doesn't fail at present conditions. But for a 25-year storm on the last pipe, it takes 80% disconnection to get that pipe to no longer fail.
We pretty much found that 80% would get it, as long as those areas aren't going into the combined sewer. For our strategic disconnection, we disconnected. We front-loaded the disconnections pretty heavily, so that we had about 80% disconnection in the first 2 blocks and about 50 in the third and 65 in the last one. This lets you get it to pass. I think it was 10-year storm.
Yeah.
This would pass a 10-year storm for the least disconnection per roof. We started from the west side of the block when we disconnected to the east.
So our conclusions were that a minimum of 80% disconnection is required to prevent failure, especially in the first 2 blocks. The houses in the first block have the most impact on the network, but these might be the least likely to disconnect because they're probably the least likely to get it back up because they're in the beginning. The worst pipe was the one in between 5th and 6th, the third pipe in the network. And incidentally, disconnections on this pipe had the least effect because we, in our strategic disconnection, we only had a 60% disconnection and the pipes no longer failed.
Well, we have a little bit of time